Can everybody see the screen? Okay. So, yeah, so let's solve some problems. Um, so, this is mostly based on the classification and logistic regression, right? So, the first um, question is like for linear classification, uh, what do we use, right? So, we have to answer the most appropriate choice here. So this is a classification problem. So the first option is like function to separate the classes, a linear function to model the data, a linear loss, and non-linear function to fit the data. Yeah. So it's a B. No. I mean we don't model the data for the classification task. Any other guesses? You can type in the response. Yeah, that's A. So basically, we use this for linear classification. We use a linear function to separate the classes, right? So the second, we don't use to model the data, right? So we want a classifier that can separate the classes and a linear loss. So loss is not linear, right? Even for classification case, and you don't fit the data, right? So that's even D is not the right answer. So yeah, so we want logic transformation for probability that x takes a value 1 for a given data. I mean it should be x. I mean there is a typo here s, but that should be okay. So here how many we have four ones and three zeros. So we want a logic transformation. So for that we need the what is the probability that x is equal to 1. So any guesses what is the probability that x is equal to 1 from this set? So yeah, so that is 4 by 7. um, right, the logic transformation is nothing but the odds of that x is equal to 1, so it's p over 1 minus p, the ratio, right? So that's it. Yeah, it's 4 by 3. It's not what I asked was probability that x is equal to 1, but logic transformation is nothing but uh, the odds basically. And yeah, so now binary class logistic regression, what is the output of your prediction? It's minus infinity to infinity, minus 1 to 1, 0 to 1, or minus infinity to 0. Any responses? Yeah, sure. I mean, you guys can speak up, because then you can clear your doubts. Mm, that's why we have this live sessions, right? C is correct. Why is that?
I think since we use the log function, right? So, see, you can model it between 0 to 1. Because whatever function we do, we finally do a logarithm to it, right? It's an
So,
exponential function that we then apply a logarithm.
uh, no, I'm not asking how do you construct the loss, right? So, what is the output of a binary regression is a what it is basically. It is a probability, right? You
Right.
directly model what is probability that your output is one given an input, right? So it is a discriminative model, right? So you are directly modeling how do you discriminate your outputs, and because you are modeling the probability directly, the range lies between 0 to 1, right?
Yeah, it's that exponential function, right? It's exponential e power something divided by 1 plus
Yeah, do you know
sigma
what do
exponential
you
whatever, right?
call that function? There is a name for it.
The classifier and the adaptation.
So basically, the output of this regression, it's a linear. You use a linear classifier, so it's just a W transpose X plus B. From there, you convert that whatever a real number that can span from minus infinity to plus infinity to squash it to 0 to 1,
Right.
right? So
Right.
what function is that? What is the name of that function we typically use?
I'm not sure.
So that is sigmoid, right? It's
Ah,
1 by 1
right.
plus e power minus x, right? Sigmoid
Hmm.
is a continuous differentiable function between in the entire real lines minus infinity to plus infinity, and it
Right.
it goes to 0 at minus infinity, it goes to plus 1 at infinity,
Right.
right? So that's why your output is a probability, uh, lies between 0 to 1, right? Right. Yeah. So, I mean, this is very simple question. Um, well, you are given log of 1 minus some probability function, and of course it's divided by 1 plus that's the same, and that is given to be that is modeled as a linear regression kind of thing, right? So, what is p of x? So, you guys can take time and tell me their answer. It is very simple. You just need to do some algebra there. The oh, it's yeah. So that's the right answer would be. So it is very simple, right? Just straightforward algebra. There is nothing much here, right? Yeah. So one another question on logistic regression. Um, so why logistic regression is considered to be robust to outliers? You can read all the options and tell me which one is the most appropriate. Uh, any guesses? Yeah, is right answer. Yeah, if the question was posed, let's say this way, linear regression, uh, considering a loss function as mean squared error, and a linear regression considering a loss value with mean absolute error. So among MSE and mean absolute error MAE, which loss function is most robust to outliers? I'm just extending some discussion on this. So just to understand why, what do you mean by robustness to outliers? So you guys got the question. So yeah, so this is a question. Question is, I mean, you have seen like the logistic regression is robust to outliers because it squashes any inputs in the range 0 to 1. Now the same question if I pose, if in a linear regression sense, and I give you two options for loss functions, one is mean squared error and other one is mean absolute error. So which one is most robust to outliers? So I see Prajakta, I mean, raised hand. Any doubts? Yeah, so which one is most more robust to outlier? So mean absolute error, or that's right, mean absolute error. Why do you think that mean absolute error is most more outlier to uh, most robust to outliers? Yeah, so basically what is happening in mean squared error, your any, let's say, any data point is far away, and and if that gets into your regression loss function, because it is squared, right? And that entire training is dominated by that outlier point, not your true data which you are supposed to learn, right? So relative to mean absolute error, mean squared error is more prone to the outlier data. So in practice, whenever you have these things, right, the best option is to filter out, if you know a priori that some data is an outlier. Otherwise, use if you don't have control over what you see, right, you can use some robust cost function such as this mean absolute error. And there is some other loss function in practice people use is a Huber loss, right? So the Huber losses, it is something, let me draw it, right? Let's say this is your, so mean squared error is something like this, right? It's a squared error. So any slight disturbance will penalize too much, right? So mean absolute error is will have something like this, right? If even if outlier data point comes around this point, right, it doesn't penalize that much. I mean, compared to this mean squared error. Now there is combination of mean uh, absolute error and mean squared error, right? That is Huber loss. So what that loss is, for very small values you consider mean squared error, right? For larger values, right, it takes mean absolute error. Right. So I mean, this things you can use in practice. I mean, in your if you're in your work, if you encounter any outliers or you don't have control, right? So Huber loss is the best. Uh, but if you can filter out all the data outliers a priori, you can use the mean squared error itself. So yeah, any questions on this these things? So you might have doubt what is this y-axis and x-axis here, right? So this is loss, your y-axis, and x-axis is the error.
Yes, I have one question.
Please, yeah.
So for all the for all the algorithms, all the data, everything that we've been looking at right now, we've only been focusing on numerical data, right? We're not touching categorical data at this point of time. We're not doing encoding of any sort to like deal with categorical data.
Categorical data, yeah, I mean there are many ways to handle categorical data.
Yeah, but we've not delved into that so far, right?
You will not,
In the lectures.
I mean you will not dealt also, you will, because that is I would say it's a more of data engineering kind of stuff rather
Yeah,
than algorithmic.
fair enough. Yeah,
So there are many ways to model. Say categorical features, you can model the 100s,
yeah.
right? And another way to model is, say, you can replace it by probability of the occurrence across your data set. Um, right. So there are many tricks to model that, but yeah, but in no way those things will what should I say, uh, will contribute to your algorithms. Underlying algorithms are the same. So in this course you mostly learn about algorithms, right? Not would definitely not the data engineering part. But having said that, that is the most important thing in practice, along with algorithms, right? Even before you go to algorithms, you have the data processing stage where you need to clean up all this data, filter out as many outliers if you can, right? So you can consider, if you want more practice, you can consider doing some coding exercises in Kaggle, uh, right? Very simple problems. There also you will see this outdoor, all kinds of features you will see, categorical and all.
All right.
What is this? Any more questions? I mean, feel free to ask. So this is, that's why this live sessions have been organized. So, what do you think of these problems? Do you want any more difficulty level to be increased, or this is fine, or what do you guys think?
Can it be decreased, or at least for us to like get some idea on how to solve the numerical problems? Because I think, at least for me, what I struggled with the most was when we were asked to do I think the principal component analysis for the previous week's question.
The last
Uh,
week, right?
yeah, so week three,
Huh, huh.
uh, trying to do the principal component analysis, I think there was a little bit of there's a slight gap in understanding between what was given in the lectures and on the assignment to what I was trying to do. So like it was given that okay, yeah, take the mean of the data, find the eigenvalues, find the eigenvectors, and all that stuff.
Right,
But
right,
then the final step of like okay, then from there the principal component value will be obvious. I'm like, where is it obvious? That so there is that last step. There was kind of a disconnect. So it is. I tried looking for it online as well. I couldn't
Mhm.
find anything. Finally, I found one video that basically said, "Oh yeah, use this code in Python to get whatever answers that you want," uh, and
No,
that's
that
how the answers
that's
were basically just ready-made, just given out of there. I didn't understand what was finally happening. So if someone could like, if some of those finer details could be like, made more
right.
obvious.
So what we can do is, maybe at the end of this, we have solved 5 questions now. Maybe we'll solve 5 more questions. You can pinpoint to me like which step you have the doubt.
Could we just go through an exercise question? Because we did have, so the deadline for week three's assignment has already passed and we've already got the solutions and the remarks for
Okay.
that.
Okay.
So can we just go through one of those practice questions that is there?
Right now I don't have it with me. If you can share, we can go through. If you don't mind sharing it. But yeah, we will complete this and we'll stop the recording.
All
Right.
right.
Then we can see that.
All right, sure. Yeah,
That's fine, right?
I can give I have the problem in front of me, so I can just, just copy paste the problem in the chat.
Yeah. Please copy paste it. Once we finish it, we'll look into it.
Perfect. Yeah. All right.
Yeah. So now we come to uh, LDA, right? Linear discriminant analysis. So this question is very simple. If you know what LDA does, you should be able to answer this. So there is more than one correct answer. To be, I mean, to give you a hint. A and D. Minimize the intra-class variability and maximize. Yeah, that's correct. So basically, what you do here is in linear discriminant analysis, uh, and the two Fisher's discriminant analysis, right? So what you do is you find a line, right, or I mean, or a hyperplane that's typically called in more than this two dimensions, right? You find such a direction so that you when you project onto it the data points onto it, your this thing, the within class variance should be as minimum as possible, and the distance between the means of the classes or the clusters, let's say, should be as far as possible, right? So that's, I mean, the cost function is designed itself is designed in that way, right? So this is very I mean, a simple thing, right? Two class data set is given, right, and it has mean 0 and 1, right? And the variance for class 0 is 2, and variance for say class 1 is 3, right? So will LDA be able to classify them perfectly? So let's draw that. uh, so this is it. uh, let's say this is 0 and this is 1, and what was that, 2 and 3 is the variance, right? So let's say your class 0 has a variance of 2, means say that means a class 0 uh, is varying from, let's say, -2 to 2, right? Class 0 points will be varying from -2 to +2, as its variance is that much, and 1 has a variance of 3, class 1, right? So here, let's say it is varying from -2, the same thing, -2 to 4, right? 1 plus 3, that is, I'm just doing one sigma thing. So typically, if you consider Gaussian, within 3 sigma, you have around 99% of your data, right? So here, if you see, the data is heavily overlapped, right? 0 is completely overlapping into 2, the class one's thing, right? So no matter what classifier you use, you cannot differentiate between 0 and 1, right? So that's, so LDA will definitely will not be able to classify them. So that's the thing. Yeah. So same problem now. You have mean 0 and 5, and variance 1 and 2. Right. So let's consider what how this will look. Let's say this is it. Means this is at 0, class 0. Let's say this is at class 5. Mean of class 5 is clustered at 5. Class 1 is clustered at 5. The variances 1 and 2, right? So 1 is, that means between minus 1 and plus 1, you have this class 0 data. And let's say this is 3 and 7, right? 3 and 7, minus 1 to plus 1. Right here you can see this data is quite separable, right? So yeah, you should be able to classify this data, right? I mean you can draw pictures for this kind of problems, that will get some intuition, right?
So yes, how do we do that for like multidimensional data? Suppose
No,
you have more than three or four dimensional data, how do we actually figure that out?
multidimensional you cannot.
So then how do we know if LDA is a good idea or not to apply for like multiple dimensional data?
Right. So what do you do is, that's where you do this visualization kind of things, right? You do PCA.
That's just
And
dimensionality reduction, right? So you'll go from say probably 100 columns to maybe 50 columns, but it's still a very large number, isn't it?
no, no, no. Why 100? You go for 2 dimensions, right? You go for 3 dimensions where you can visualize, right?
So, but won't that increase the errors also?
Yeah, it does increase, but you get a fair idea of how your data is, right?
Will you be doing any questions that involve something like this later on in the course?
So see, one straightforward way to visualize that is, you know, is to reduce your dimension to 2 and just have a scatter plots and see data points belonging to one class are being clustered or not, right? That's one way. And the other way around is, it's more complex, that's called as t-SNE
Sorry,
plots. T-SNE, it's called as t-SNE plots. You can look up that.
could you spell it?
I'll write in the chat box. Just t-SNE. Okay. So T is stochastic neighborhood embeddings, right? So that's a non-linear embeddings, right? So PCI is linear,
Right.
and it gives even much better, visualization. Um, so see, that's one thing, right? So what happens is, you are given, let's say, a binary classification problem, and you are asked to figure out if it works or not, right? So typically, what do? You don't know what is the best model. You start with a simple model, say linear. Uh, say logistic regression, say a linear model. You don't solve that problem, right? You go for some more complex models. Say you go for neural networks, right? So it depends on the complexity of the problem, right? So you don't know a priori that uh, um, the data is separable or not, and you don't know what is the right model to use also, right? So in practice you explore all the options.
All right.
Right, so this is the question, right? You're given two classes, pluses and minus, right? And now, what is the best uh, line to project the data? make so you can remember two things. LDA uh, should result in the maximizing your means of the two classes, and at the same time it should minimize your within class variance, intra class variance. So which line uh, does the thing?
Sir, orange.
No, that's the that I would say that should be the least choice.
It's blue, right?
Yeah, that's blue. You can see, right, if you project all the data points onto this blue line, you get a perfectly separable you draw a line perpendicular to that on the projected data. You can separate those two clusters with maximum difference among all the possible options, right? So what I was saying earlier is, let's say you have more dimensions, right? Say, so this plus data point, let's say it lies in some whatever 50 dimensions, right? So use your PCA and reduce it to 2 dimensions and plot and then visualize. Uh, if it is really separable, you should see it. If not, you should use your uh, I mean, there is no one correct answer at hand. So you should try other models, like complicated models like neural networks and all, and then check, or decision trees or those kind of things, random forests. So we're coming to the last thing. Yeah. So LDO assumes that the class data is distributed as Poisson, uniform, Gaussian. So what do we assume typically in LDO? So I think LDA has been is completed by this week, right? In the course.
LA was covered in week 3. Week 4 is about support vector machines, and
Okay,
week five was, I think, released just today, and that's about only it's about artificial neural networks.
right. So yeah, I think probably then next week we'll discuss support vector machines. Or you want to discuss week 5 so that it helps you solve problems, assignment problems.
I think we had to like try to figure out week 4 first before we go to week 5, because that deadline is coming up, right?
Yeah, the Gaussian and the summon type, that is true. Um, yeah, I think that's pretty much I had to cover today. Um, yeah. So any doubts regarding logistic regression in particular?
Can you give us a little brief about the whole forward stepwise selection, backwards and forward stagewise and all that? Just a brief, just like distinction between all of those.
So basically, in forward stepwise, what happens is this thing, right? It you need to find the best features. Let's say you are given some 100 features, right? So what do you do is You do a search of the 100. You pick, say, feature one and fit the data, right? You measure some loss, mean squared error loss or MA, whatever, in whatever uh, sense you call it as best, right? For all the 100 features, right? Now, whichever is the best, take that and keep it aside. Now, among the remaining 99, again you try to fit, right? So again, whichever gives you the best, then you and keep adding that thing. So that's the forward stage selection. A backward selection, what do you do is you fit a model with all the 100 features, right? And whichever, and you keep removing one by one these features, and whichever gives you a maximum drop in the accuracy, that is the most important feature for you.
Whichever feature gives the maximum drop in accuracy.
Right. Whichever, by removing the feature, if you see a maximum drop, right? So that means
Okay.
that feature is the most important.
Okay. So we keep that.
Yeah, yeah, you should keep it. But to know, you should drop one by one, right?
Okay.
Let's say you have 10, and let's say feature 7 has resulted in maximum drop in accuracy. So
Okay.
feature 7 is most important for you.
Right.
Then among the 1 to 10 without 7, you have 9
Right.
features. You repeat this
Right.
process again.
So then which one do you drop? So if you found out that seven causes the most
Hmm.
drop in accuracy, if you drop it,
Hmm.
you still have nine other features that you have to drop, right? Like one of
Yeah,
them
yeah, yeah.
how many were?
Yes. So,
This is this is stage-wise selection.
yes. So it's a forward and backward. So we are talking about backward now.
No, no, stage-wise or stepwise.
I think it's stepwise. Stage wise is somewhat different, where you measure with respect to residuals. That is bit more complex.
Can you please explain the difference between? Now we understood this stepwise.
Yeah, yeah.
Can you please give some more idea about stage-wise selection?
Yeah. So basically, what is happening is the first step is, let's say you are forward stepwise. You identify the best feature, right? In the stage wise also, you do the same thing. Um, you find the best feature, and what you do is after finding the best feature, you measure the error by regressing on the best feature, right? On the error, you again regress on the remaining features. So what I can do is I can put a slide in the next week explaining that, because I don't have anything to show currently, right?
Yeah, yeah, please, because that part was still a part of confusion. So
Right, right.
that
So thing you can just uh, I mean, to remember intuitively, a forward stepwise is like adding features one by one, which keeps increasing the accuracy the most. Backward stepwise is the reverse. You keep dropping the features, which drops your accuracy the most. Stage wise is where you keep fitting your features to the residuals. So these three are very much different. Right? I'll put a slide on these three the next week.
Should I give you the PCA problem?
So we can wait for till 11 if anyone has any questions on this thing. So this one versus all and one versus one. This you guys are clear about this those aspects, right?
Sorry.
So let's say you are given a binary logistic regression classifier, and you are asked to do a 10 class problem, right? So what are the strategies? So last week I think we discussed this thing briefly. Um,
I
so
think
you
the
can
idea was to do like logistic, like do it for each of those classes and then pairwise and stuff like that, something like that.
right. So those things you guys are clear, right? Yeah, one versus one and one versus rest. So which one is better? Which one is computationally efficient? Yeah. So one versus one is like pairwise options, right? So for a 10 class problem, yeah, you're right. So one versus rest is best to uh, pinpoint the exact numbers. So the number of binary classifiers you needed for one versus one is 10 choose 2. That is like how many? 45 or 55? Um, I think 45, yeah. And one versus rest, you only need 10 of them. In practice, you don't do either of those because you directly want to have a 10 class classifier, right? So yeah, if we don't have any more questions, I think I will stop recording and on for this week, and I can take the this PCA based question. Okay.